Earth's atmosphere is continuously bombarded by cosmic rays, some of which cause transmutation of some atoms in the upper atmosphere. A result is a spraying of protons and neutrons into the atmospheric environment. Most of the protons are stopped as they collide with the atoms of the upper atmosphere, stripping electrons from these atoms to become hydrogen atoms. But many of the neutrons produced collide with and are captured by atoms in the denser lower atmosphere. One such reaction is a neutron colliding with a nitrogen nucleus. We see that in a typical reaction, a nitrogen capturing a neutron emits a proton to become the nucleus of a carbon isotope, carbon-14. This carbon-14 isotope, which makes up about 1/1,000,000th of the carbon in the atmosphere, has 8 neutrons and is radioactive. The most common isotope, carbon-12, has 6 neutrons and is not radioactive. Because both carbon-12 and carbon-14 are forms of carbon, they have the same chemical properties and both can chemically react with oxygen to form carbon dioxide, which is taken in by plants. This means that all plants contain a tiny bit of radioactive carbon-14. All animals eat plants, or other animals that ate plants, and therefore have a little carbon-14 in them. In short, all living things on Earth contain some carbon-14. That means you and I are radioactive. Who would have thunk that in the old days? Carbon-14 is a beta emitter and decays back to nitrogen as we see here. Do you know about carbon dating? The process that tells the ages of the Dead Sea Scrolls and other ancient objects? Well, this is it. Living plants continually take in carbon dioxide as long as they live. Whatever carbon-14 is lost by decay is immediately replenished with fresh carbon-14 from the atmosphere. The result is a radioactive equilibrium, a constant ratio of about 1 carbon-14 atom to every trillion carbon-12 atoms. When a plant or other organism dies, replenishment of carbon-14 stops. Then the percentage of carbon-14 decreases at a constant rate given by its half-life. The longer a plant or other organism is dead, the less carbon-14 it contains relative to the constant amount of carbon-12. The half-life of carbon-14 is about 5,730 years. This means that amount of radioactive carbon-14 in the skeleton diminishes by 1/2 every 5,730 years, with the result that today the skeleton contains only a fraction of the carbon-14 it originally had. The red arrows symbolize relative amounts of carbon-14. For anything organic, half its carbon-14 atoms that remain after 5,730 years will then decay in the following 5,730 years, and so forth. Can you see how scientists can calculate the age of carbon-containing artifacts, like the skeleton shown here? They compare its radioactivity to the current level of radioactivity for equal amounts of old and new carbon. Suppose, for example, that an archaeologist takes 10 grams of carbon from the wood of an ancient ship and finds it 1/2 as radioactive as 10 grams of carbon taken from any source currently interacting with the air. 1/2 as radioactive? Isn't the half-life of carbon-14 5,730 years? Then the ship is some 5,730 years old. And if the radioactive count for the ancient carbon was 1/4 as much, the ship would be 2 half-lives old, about 11,500 years old. This is assuming the ratio of carbon-14 to carbon-12 was about the same when the ship was made as it is now. In any event, you have an approximate age, very young. This carbon dating process enables us to probe as much as 50,000 years into the past. Beyond this time span, there is too little carbon-14 remaining to permit accurate analysis. Carbon-14 dating would be a relatively simple and accurate dating method if the amount of radioactive carbon in the atmosphere had been constant over the ages. but it hasn't been. Fluctuations in the sun's magnetic field, as well as changes in the strength of Earth's magnetic field, affect cosmic ray intensities in Earth's atmosphere, which in turn produce fluctuations in the production of carbon-14. In addition, changes in Earth's climate affect the amount of carbon dioxide in the atmosphere, as do the burning of fossil fuels and the testing of nuclear weapons. The oceans are great reservoirs of carbon dioxide. When the oceans are warmed, they release more carbon dioxide into the atmosphere than when they are cooler. The dating of older non-living things is accomplished with radioactive minerals, such as uranium. The naturally occurring isotopes U-238 and U-235 decay very slowly and ultimately become isotopes of lead, but not the common lead isotope Pb-208. For example, U-238 decays through several stages to finally become Pb-206, whereas U-235 finally becomes the isotope Pb-207. Lead isotopes 206 and 207 that now exist in uranium ore were at one time uranium. The older this uranium-bearing chunk of granite rock, the higher the percentage of these lead isotopes. From the half-lives of the uranium isotopes and the percentage of lead isotopes in the uranium-bearing rock, calculations can be made to estimate the date at which the rock was formed. All yum physics. I want to leave you with a question. First, let's suppose that you join a group of archaeologists and find an ancient wooden bowl. If you extract 1 gram of carbon from the wooden bowl and find it 1/4 as radioactive as the same amount of carbon taken from a freshly cut tree branch, what is the likely age of the bowl? Until next time, good energy.